In the vast expanse of our cosmic neighborhood, orbiting the majestic ringed planet Saturn, lies a world of stark contrasts and scientific mysteries, Dione. Named after the Titaness of Greek mythology, Dione's bright, reflective surface hides ancient scars and geological wonders. It's the fourth largest in a system of over 200 known satellites. By diameter, a mere 1,120 kilometers wide, smaller than the width of Texas. Yet despite its modest size, this frozen world holds secrets that continue to captivate planetary scientists and astronomers alike. Today, we journey to this distant moon, a place where icy cliffs rise above cratered plains, where mysterious wispy terrains streak across the surface, and where the forces of orbital resonance have shaped a world unlike any other. I'm Alex McColgan, and you're watching Astrum, and this is Dione, Saturn's fractured moon. Like many of Saturn's moons, Dione's discovery dates back to the dawn of telescopic astronomy. It was first spotted by the renowned Italian astronomer Giovanni Cassini on the 21st of March 1684. Cassini, working from the Paris Observatory, had already discovered Saturn's moon Iapetus 2 years earlier, and would go on to discover two more of Saturn's moons, Rhea and Tethys. Initially, Cassini simply called it Saturn IV, denoting it as the fourth moon of Saturn in order of distance. It wouldn't be until 1847 that English astronomer John Herschel suggested using the names of Titans from Greek mythology for Saturn's moons, and thus Dione received its mythological name. The name is fitting. In Greek mythology, Dione was a Titaness, often described as the daughter of Oceanus and Tethys, and sometimes considered one of the consorts of Zeus. Some myths even suggest she was the mother of Aphrodite. Like its mythological namesake, the moon Dione would turn out to have surprising connections and relationships to other bodies in the Saturnian system, but more on that later. For nearly 3 centuries after its discovery, Dione remained little more than a point of light in our telescopes, a mysterious world about which we knew virtually nothing. Even with Earth's most powerful observatories, this distant moon revealed few of its secrets. All of this would change dramatically with the dawn of the space age. Our first close glimpse of Dione came from NASA's Voyager 1 spacecraft, which flew by the Saturnian system in November 1980. As Voyager approached, Dione began to transform from a mere dot of light into a world with distinct features and character. The Voyager images, though limited by the technology of the time, revealed a moon with a complex surface. Dione appeared heavily cratered on its trailing hemisphere, the side that faces away from its direction of orbit. The largest of these impact craters is Evander, a basin approximately 350 kilometers in diameter. Other significant craters include Ennius and Dido, named after characters from Virgil's Aeneid. But perhaps most intriguing were the strange bright streaks that crisscrossed portions of its surface. These features, which scientists dubbed wispy terrain, appeared unlike anything seen on other worlds at that time. But with the limited flyby and imaging capabilities, Voyager could only whet our appetite for knowledge about this enigmatic moon. The spacecraft measured Dione's diameter at about 1,120 kilometers, making it Saturn's fourth largest moon after Titan, Rhea, and Iapetus. Voyager also determined that Dione has a density of about 1.48 grams per cubic centimeter, suggesting a composition primarily of water ice with a modest rocky component, likely containing a small silicate core. But the brief encounter left planetary scientists with more questions than answers. What were those mysterious wisps? How did Dione's surface evolve? What forces shaped this distant world? It would take another spacecraft, bearing the name of Dione's Italian discoverer from 400 years ago, to truly begin to unravel these mysteries. In July 2004, NASA's Cassini spacecraft entered orbit around Saturn, beginning what would become a 13-year mission of discovery throughout the Saturnian system. This sophisticated spacecraft carried a suite of scientific instruments that would revolutionize our understanding of Saturn and its moons, and Cassini conducted several close flybys of Dione during its mission, coming as close as 99 kilometers to the moon's surface. These encounters provided unprecedented high-resolution images and a wealth of scientific data about this mysterious world. One of the most significant discoveries came when Cassini revealed the true nature of the mysterious wispy terrain first glimpsed by Voyager. What had appeared as bright, streaky deposits from a distance were actually exposed ice cliffs, the faces of enormous faults cutting through Dione's icy crust. These features, now called chasmata, are in some cases hundreds of kilometers long and several kilometers deep. The most prominent of these features is Palatine chasmata, a massive system of fractures stretching more than 600 kilometers across Dione's surface. Other major fracture systems include Padua chasmata and Carthage fossae. In some places, these fractures cut through craters and other surface features, indicating they formed relatively recently in Dione's geological history. Dione's density measurements from the Cassini mission confirmed that it is composed primarily of water ice with a significant rock component, roughly 40% rock and 60% ice by mass. This gives Dione a mass of about 1.1 times 10 to the power 21 kilograms. Based on this density and mass, scientists confirm the belief Dione likely has a differentiated interior with a modest rocky core surrounded by a thick mantle of ice. The surface temperature of Dione is extremely cold, averaging about minus 187 degrees Celsius. At those temperatures, water ice behaves like rock does on Earth, allowing for the formation of solid geological features like mountains, craters, and canyons. As mentioned, half of Dione's surface is pocked with craters, signs of ancient impacts. But perhaps more intriguing than the craters are the areas where craters are notably absent. Certain regions of Dione show evidence of resurfacing, geological processes that have erased older features and created smoother plains. These areas, primarily on the leading hemisphere, suggest that Dione has experienced periods of internal activity that has refreshed parts of its surface. But let's talk more about Dione's chasmata. This bright ice stands in stark contrast to the surrounding older surface material, which has been darkened by exposure to radiation and micrometeorite impacts over billions of years. But what caused these enormous fractures? The leading theory is that they formed in response to global stress patterns in Dione's icy crust. As Dione cooled and evolved over billions of years, its crust would have experienced tension and compression forces that ultimately led to fracturing. Some scientists believe these fractures may be evidence that Dione once had a subsurface ocean that froze over time. As water expands when it freezes, the growth of ice would have placed enormous stress on the outer crust, potentially causing it to crack in the patterns we see today. Others suggest that tidal flexing, the stretching and squeezing of Dione due to Saturn's gravitational pull, may have generated enough heat and stress to create these features. We still don't have the full answers. Dione orbits Saturn at a distance of about 377,400 kilometers, completing one orbit every 2.7 Earth days. Dione is tidally locked to Saturn, meaning the same side always faces the planet, just as our moon always shows the same face to Earth. Like many moons in the Saturnian system, Dione participates in a global dance of orbital resonances that has profound implications for its evolution. Perhaps the most significant of these relationships is the 2-1 mean motion resonance Dione shares with Enceladus. This means that for every orbit Dione completes around Saturn, Enceladus completes exactly 2 orbits. This is not merely a coincidence. It's a gravitational relationship that has locked these two moons into a synchronized pattern that affects both worlds. This resonance creates tidal forces that generate heat within both moons. However, the effects are much more dramatic on Enceladus, which shows extraordinary geologic activity, including its famous southern polar geysers that continuously erupt water ice into space. Dione, being larger, experiences proportionally less tidal heating from this relationship. And did you know Dione also has its own small satellites? Two tiny moons named Helena and Polydeuces orbit Saturn at the same distance as Dione. These moons occupy what is known as Lagrange points in Dione's orbit, stable gravitational points that precede and follow Dione as it circles Saturn. These tiny moons, sometimes called Trojan moons, are just a few kilometers across and are likely captured or formed from debris in Dione's orbital vicinity. But what about that subsurface ocean? The possibility is certainly intriguing. Scientists are always fascinated with any such location around the solar system due to all oceans' potential to be the birthing place of life. So the existence of an ocean would be significant on Dione, and it's not without evidence. Cassini's magnetometer detected a weak interaction between Dione and Saturn's magnetosphere, which some scientists interpret as evidence for a conductive layer beneath the surface, possibly a salty subsurface ocean. The extensive fracture systems on Dione's surface also suggest significant geological activity in its past, which could have been driven by the presence of liquid water below. Models of Dione's internal heat budget, considering radioactive decay in its rocky core and tidal heating from its orbital resonance with Enceladus, suggest it may have generated enough heat throughout its history to maintain a liquid layer between its core and icy crust. If Dione does harbour a subsurface ocean, it would join a growing list of ocean worlds in our solar system, places like Europa, Enceladus, and possibly Titan, that could potentially provide habitable environments for simple forms of life. However, unlike Enceladus with its dramatic plumes of water vapor erupting into space, Dione shows no current signs of geological activity that would provide easy access to any subsurface ocean. If an ocean exists within Dione, it remains well hidden beneath kilometers of ice. Since the end of the Cassini mission in 2017, when the spacecraft was deliberately plunged into Saturn's atmosphere, no other spacecraft has visited the Saturnian system. This means our current understanding of Dione is based entirely on the data collected during these limited encounters with Cassini and Voyager. However, the scientific community has proposed several concepts for future missions to the Saturn system that could include further exploration of Dione. These include orbiter missions that would study multiple moons of Saturn, landers that could touch down on Dione's surface, and even specialized missions to search for signs of a subsurface ocean. One particularly ambitious concept is the Enceladus orbiter, which would primarily study Enceladus, but could potentially make multiple flybys of Dione as well. Another proposal, called the Journey to Enceladus and Titan, would similarly focus on those two moons, but include observations of Saturn's other major satellites, including Dione. While none of these mission concepts have been approved for development, the scientific questions raised by our limited exploration of Dione ensure that it remains a compelling target for future study. As we draw back from our close examination of Dione, we're left with a portrait of a world of fascinating contrasts. A moon whose seemingly static, icy surface tells a story of a dynamic past. The extensive networks of bright fractures that crisscross its surface speak to powerful forces that have shaped and reshaped this world throughout history. The striking difference between its cratered trailing hemisphere and smoother leading face hints at ongoing processes that continue to sculpt its features, and subtle clues in its gravitational and magnetic signatures whisper the possibility of a hidden ocean below its frozen exterior. In many ways, Dione exemplifies the surprising complexity we've discovered throughout Saturn's system of moons. What once appeared as mere points of light in our telescopes have been revealed as unique worlds with their own geological characters and evolutionary histories. These discoveries challenge us to rethink our understanding of what drives geological activity in the outer solar system, where the heat of the sun is too distant to power the processes we see on Earth. In the vast symphony of Saturn's moons, Dione plays its own distinct melody, one that continues to fascinate and inspire us to look deeper into the mysteries of our solar system. Can a moon vanish? It turns out it is possible. In the early days of astronomy, the Saturnian moon Iapetus routinely appeared to vanish from sight entirely. Some days it was there, and the next it was gone. This was the ultimate magician's trick, but as we figured out how it was done, Iapetus's mysteries only grew deeper. That is because Iapetus is a place of profound contrast, one half plunged into near absolute darkness, and the other half gleaming with the brilliance of reflective ice. Around its equator, a colossal mountain range, a stony girdle wrapped precisely around its equator, whose origins defy explanation. Why does this moon present such a dramatic, two-faced characteristic? What cataclysmic event or slow, inexorable process could have sculpted a mountain chain taller than Mount Everest in a place that defies explanation? And what secrets does this distant world hold about the turbulent youth of our solar system? I'm Alex McColgan, and you're watching Astrum. Join me today as we journey to Iapetus, Saturn's third largest moon, and arguably its most enigmatic. Our story begins with the keen eye of Giovanni Domenico Cassini. In 1671, using the refracting telescopes of the Paris Observatory, Cassini spotted a new point of light orbiting the ringed giant. But this new moon behaved strangely. When it was on the western side of Saturn in its orbit, it was reasonably visible. But as it traveled to the eastern side, it seemed to vanish, becoming incredibly faint, often disappearing entirely from view in those telescopes. Reflecting on his observations, Cassini remarked that sometimes after having begun to disappear with the 32-foot telescope, it has been sought in vain the next day with one of 45. Cassini concluded that this moon must have one hemisphere that is significantly darker than the other, and it must be tidally locked to Saturn, always keeping the same face towards its planet, just as our own moon does towards Earth. This meant that as Iapetus orbits Saturn, it alternates in presenting its bright face and its dark face towards Earth. When the bright side faced us, on the western side of its orbit from our perspective, it was visible. When the dark side faced us, on the eastern side, it faded from view. It was an astonishing observation for the 17th century, and marked the first surface property ever detected on a planetary moon outside the Earth-Moon system. Cassini named the four moons he discovered Sidera Laodicea, or the Star of Louis, in honor of King Louis XIV, but these names didn't stick. Later, John Herschel suggested names from the Titans, brothers and sisters of Saturn in mythology. Iapetus, the father of Atlas and Prometheus, and by extension, father of Prometheus's creations, mankind became the moniker for this peculiar world. For centuries, Iapetus remained little more than a point of light exhibiting this bizarre brightness variation. Even the Voyager probes, which revolutionized our understanding of the outer solar system in the late 1970s and early 1980s, only managed distant flybys. Voyager 1 captured images showing the dark brightness difference, confirming Cassini's deduction, but the resolution wasn't high enough to reveal the intricate details. Voyager 2 fared slightly better, passing closer and giving us our first tantalizing glimpse of another astonishing feature, a hint of the massive ridge near the equator. But the full picture, the breathtaking weirdness of Iapetus, would have to wait for the arrival of a dedicated Saturn explorer. Enter the Cassini spacecraft, named, fittingly, after the moon's discoverer. Arriving at Saturn in 2004, the Cassini mission would spend 13 years unveiling the secrets of the ring planet and its diverse family of moons, and Iapetus was high on its list of targets. Cassini's observations, particularly a close, targeted flyby in September 2007 that brought the probe within just 1,640 kilometers of the surface of Iapetus, transformed the moon from a distant glint into a complex world we could finally study. Iapetus is a moon with a low density, just 1.2 times the density of water, suggesting that it's composed of up to 75% water ice. Its shape is not perfectly spherical, partially due to the equatorial ridge, giving it that distinctive, oblate, walnut-like appearance. It likely doesn't possess a subsurface ocean like Enceladus or Europa, as there's no evidence of recent geological activity or the tidal heating needed to maintain liquid water deep beneath its icy shell. Its surface is ancient, cold, and heavily cratered, particularly in the bright regions of Roncevaux Terra, testifying to billions of years of bombardment. Its orbit is also unusual. Iapetus orbits much farther out than other Saturnian moons, at an average distance of about 3.5 million kilometers, more than twice the distance of the next major moon, Titan. This large distance means it takes 79.3 Earth days to complete one orbit around Saturn. Crucially, its orbit is also slightly inclined, tilted by about 15 degrees relative to Saturn's equatorial plane, where most other major moons orbit. This distance means Iapetus is less affected by Saturn's magnetosphere and the intense radiation belts closer to the planet. Its orbital inclination might be a clue to its formation or early migration history, possibly indicating it didn't form with the same equatorial disk as Saturn's closer, regular moons. But let's turn to the aspect of Iapetus that makes it so fascinating to look at: its surface. Iapetus is cleanly divided into two distinct regions. The leading hemisphere, the side that faces forward as Iapetus orbits Saturn, is incredibly dark. This region is known as Cassini Regio, and it covers about 40% of Iapetus' surface. Its albedo, the measure of how much light it reflects, is extremely low, somewhere between 0.03 and 0.05. That's as dark as asphalt or coal dust. It absorbs almost all the light that falls on it. In stark contrast, the trailing hemisphere, the side facing away from the direction of orbit along with the poles, is incredibly bright. This region, encompassing Roncevaux Terra to the north and Saragossa Terra to the south, boasts an albedo of 0.5 to 0.6, as bright as freshly fallen snow or brilliant water ice. This almost tenfold difference in albedo is the greatest interhemispheric albedo contrast that we know of in the solar system. Imagine seeing this world up close, one side a deep reddish brown or black, the other a dazzling white. In some areas, particularly near the equator, the boundary between those halves can appear remarkably sharp, as if painted on. In other areas, especially at higher latitudes, the transition is more gradual, with bright rayed craters splattered across the dark terrain and dark streaks dusting the bright terrain like splashes of mud on snow. This image from Cassini vividly shows this contrast. It is a world literally split down the middle. So, what causes this yin-yang appearance? For a long time, the leading theory proposed an internal origin, perhaps some form of dark, cryovolcanic material erupting from Iapetus' interior and coating one side. A paper reviewing the Voyager data from Bradford Smith and his colleagues in 1981 argued for this theory, identifying this ring shape as a crater partially flooded with dark, eruptive material as supporting evidence. However, Cassini's radar and imaging data revealed that the dark material forms a relatively thin layer, perhaps only tens of centimeters to a meter thick in most places. Furthermore, impact craters within Cassini Regio often excavate bright, icy material from underneath, punching through the dark veneer. This strongly suggested the dark stuff wasn't welling up from below, but was being deposited from above. A paper in 1982 made spectrophotometric observations of the dark leading surface and found that the composition of material was carbonaceous, similar to that of the Murchison C2 meteorite, which fell to Earth during a shower in 1969. To explain this finding, the authors looked to potential culprits close to Iapetus within the Saturn system. The prime suspect? Dust from Saturn's outer, irregular moon, Phoebe. Phoebe is a relatively large, dark moon captured by Saturn's gravity, orbiting the planet in the wrong direction, a retrograde orbit at a great distance. Over billions of years, impacts on Phoebe and other small, dark, retrograde moons have kicked up a vast, tenuous ring of dark dust particles. The sun's radiation exerts pressure on these dust particles, causing what is known as the Poynting-Robertson effect. As a result, this dust spirals inwards towards Saturn, also moving in a retrograde direction. Now, back to Iapetus. It orbits Saturn in a prograde direction, the same direction as Saturn's rotation and most other moons, but its orbit is significantly further out than the main rings and closer moons. As it journeys around Saturn, its leading hemisphere essentially plows head-on into this incoming stream of retrograde dark particles originating largely from the Phoebe group. It's like driving through a swarm of insects. They mostly splatter on your front windshield. The trailing hemisphere, shielded by the moon itself, collects far less of this dark material. But deposition alone doesn't fully explain the intensity of darkness we see on the leading side of Iapetus, or the complexity of the border between dark and bright. This is where thermal segregation and water-ice sublimation come into play. The dark material deposited on the leading hemisphere absorbs more sunlight than the surrounding bright ice. This causes the surface temperature to rise slightly. Iapetus is incredibly cold, but even a small temperature increase is enough to cause the volatile water ice to sublimate, turning directly from solid ice into water vapor gas. This sublimating water vapor doesn't just disappear. Because Iapetus rotates very slowly, its day is about 79 Earth days long, matching its orbital period, daytime temperatures are higher, and the ice has plenty of time to sublimate away from the warmer, dark areas. In fact, sublimation on Iapetus is so fast, if its surface were pure ice, we would see over 100 meters of ice lost to sublimation in a billion years. But that's still faster than any Saturnian satellite. But where does the ice go? It preferentially recondenses and freezes onto the coldest available surfaces. These are the already bright, icy regions on the trailing hemisphere and near the poles, which reflect more sunlight and stay cooler. Scientists suggest that due to its negligible atmosphere, sublimating molecules follow ballistic trajectories, jumping impressive distances to the trailing hemisphere in the style of a missile. This creates a runaway positive feedback loop. Dark areas get slightly warmer, lose their ice, become even darker as the underlying dark dust concentrates. They absorb more heat and sublimate more ice. Bright areas stay cold, collect migrating frost, becoming even brighter, reflect more sunlight, stay even colder, and collect more frost. Over millions and billions of years, this process has dramatically sharpened the boundary between the dark leading hemisphere and the bright trailing hemisphere, leading to the extreme contrast we see today. So the Great Dichotomy seems to be a combination of external pollution from retrograde moons and an internal sorting mechanism driven by sunlight and ice sublimation. A truly remarkable example of planetary processes at work. But the two-tone coloration is only part of Iapetus' strangeness. As Voyager 2 hinted at, and Cassini confirmed in stunning detail, Iapetus possesses another unique feature in the known solar system, a colossal equatorial ridge. This ridge is effectively a wall of mountains, stretching for around 1,600 kilometers, at least halfway around the moon's circumference. On average, it is about 200 kilometers wide at the base and reaches towering heights of up to 20 kilometers above the surrounding terrain. That's significantly taller than Mount Everest. And the most baffling part, it follows the equator almost perfectly, primarily confined within the dark Cassini Regio, although more equatorial mountains identified by Voyager on the trailing hemisphere could be a continuation of this structure. In images like this one, taken by Cassini during its close flyby, the scale is breathtaking. It gives Iapetus a distinct walnut shape. What could have possibly formed this belt of mountains? This is one of the biggest ongoing mysteries of Iapetus. Several hypotheses have been proposed, each with its own strengths and weaknesses. One leading idea suggests the ridge is a relic of a much faster spinning past. Recent models have suggested that early in its history, shortly after formation, Iapetus might have been rotating much more rapidly, perhaps completing a rotation in around 16 hours. This rapid spin would have increased oblateness, causing the moon's equatorial regions to bulge outwards due to a centrifugal force, while the moon was still young and relatively plastic or partially molten. As Iapetus cooled and solidified, this equatorial bulge froze in place. Later, gravitational interactions with Saturn slowed the moon's rotation down over millions of years until it became tidally locked, rotating only once per orbit, or 79 days. As it slowed, the centrifugal force supporting the bulge diminished, and the now solid crust couldn't fully relax back into a sphere. The material essentially slumped downwards, piling up near the equator to form the massive ridge we see today. This theory fits well with the ridge's equatorial location and its ancient, heavily cratered appearance, suggesting it formed very early on. However, it requires Iapetus to have spun incredibly fast, possibly close to its structural breakup speed, and to have solidified while maintaining that bulge. Another intriguing hypothesis proposes that the ridge is the result of material falling onto Iapetus from an external source, specifically the collapse of a sub-satellite or a ring system that once orbited Iapetus itself. If Iapetus possessed a debris ring early in its history, perhaps sourced from a captured body or a large impact, this material would naturally orbit above its equator. If this ring became unstable, or if Iapetus migrated slightly in its orbit, the ring material may have been pushed just beyond the Roche limit, which is the point at which the tidal effects of a large body overwhelm the internal gravity of a smaller one. This may have caused the ring material to slowly rain down onto the surface of Iapetus, piling up preferentially along the equator. This could potentially explain why the ridge seems most prominent on the dark leading hemisphere if the ring material itself was dark, or its deposition coincided with the influx of dark dust from Phoebe. Some models suggest that even a small moonlet breaking up within Iapetus' Roche limit could provide enough material. While elegant in explaining the location, the exact mechanisms for forming and then collapsing such a ring are still debated. Other theories, such as tectonic processes or convective upwelling from the interior, struggle to explain why the activity would be so narrowly confined to the equator over such a vast distance. A giant impact is also unlikely to produce a long, linear, and perfectly equatorial feature. Cassini's detailed images show the ridge is heavily cratered, confirming its ancient origins. It appears to be structurally composed of icy, crusty material. Some sections show evidence of landslides and collapse features. Whatever the process, it must have happened very early in Iapetus' history, perhaps within the first few 100 million years of the solar system's formation. The ridge stands as a monumental memento of Iapetus' dynamic youth, a frozen record of processes we are still striving to understand. So, what do we know about Iapetus? More than we used to, but less than we'd like. The Cassini mission fundamentally changed our perception of this fascinating moon. Its close flyby provided the data that solidified the exogenic dust and sublimation theory for the planet's two faces. It gave us astonishing, high-resolution views of the equatorial ridge, allowing detailed study of its structure and morphology, even if its origin remains debated. Cassini measured Iapetus' shape, gravity field, and surface composition with unprecedented accuracy. Without Cassini, Iapetus would have largely remained the faint, perplexing point of light it was for centuries. And yet, there are still so many mysteries. What is the true origin of Iapetus' ridge? What is the dark material of Iapetus' mysterious face actually composed of, beyond something simply carbonaceous? Unless we go there, it will be difficult to know for sure. No missions are currently planned to sample or even circle this perplexing place, so for now, we remain in the dark. Which feels appropriate. After all, as I said at the beginning, Iapetus was once the ultimate vanishing act, and a magician never reveals his secrets. In the vast expanse of our solar system, orbiting the ringed giant Saturn, lies a world of ice and mystery. This is Rhea, Saturn's second largest moon. Although you're more likely to have heard of its larger sibling Titan, Rhea is a fascinating place in its own right and harbours many secrets and wonders. Ice cliffs, hundreds of meters high, an internal structure that defies scientific models, and the enigmatic discovery that lingers around this moon that's equally as strange as the thing we didn't find. It's time for this lesser-known moon to step out from its larger sibling shadow. Let's learn all there is to know about Rhea. I'm Alex McColgan, and you're watching Astrum. Join me today on a voyage of discovery to the Saturnian system and the moon Rhea, to see what scientists have discovered there and to witness its beauty for ourselves. Rhea was discovered on the 23rd of December 1672 by Giovanni Domenico Cassini, the Italian astronomer who made numerous contributions to our understanding of Saturn and its moons. Named after the Titan goddess Rhea in Greek mythology, this moon has been a subject of fascination for astronomers and planetary scientists for centuries. Let's start with the basics. Rhea is the second largest moon of Saturn, after the mammoth Titan. With a diameter of 1,528 kilometers, it's roughly half the size of our own moon. If we were to place Rhea next to Earth, it would stretch from London to Warsaw. Rhea orbits Saturn at a distance of about 527,000 kilometers, completing one orbit every 4.5 Earth days. It's locked in a synchronous rotation with Saturn, meaning the same side always faces the planet, a common feature among large moons in our solar system. The surface of Rhea is one of the most reflective in our solar system, with an albedo of 0.7. This means it reflects 70% of the sunlight that hits it, appearing bright white against the backdrop of space. This high reflectivity is due to its composition. Rhea's surface is primarily made of water ice. But this doesn't make it a featureless ice sheet. Far from it. The moon is heavily cratered, telling a story of ancient impacts and a long, violent history. The largest of these craters, named Mamaldi, spans an impressive 480 kilometers in diameter, about the distance from Paris to Amsterdam. These craters aren't just scars on Rhea's surface, they are windows into the moon's past and composition. Observations have shown that the bottoms of some craters appear darker than the surrounding terrain. This could indicate that impacts have excavated material from beneath Rhea's bright surface, possibly exposing darker, amorphous water ice and impact melt. In this photo, you can see a crater in the southern hemisphere of Rhea, surrounded by bright ejecta. But one of the most intriguing features of Rhea is its system of bright, wispy streaks that crisscross its surface. These were first observed in detail by the Voyager space probes in the early 80s, but their true nature wasn't understood until the Cassini mission provided high-resolution images decades later. Initially thought to be deposits of frost or ice, these wisps were revealed to be ice cliffs, some hundreds of meters high. They are likely the result of tectonic activity in Rhea's past, where the icy crust fractured and some sections were thrust upward. These features give us clues about the moon's geological history and the processes that have shaped its surface over billions of years. But Rhea's mysteries don't end at its surface. In 2010, data from the Cassini spacecraft led to a surprising announcement. Rhea appeared to have a tenuous atmosphere or exosphere. A small amount of gas around Rhea is expected, but it was unexpected that there is enough to be measurable. The detected atmosphere consisted primarily of oxygen and carbon dioxide, with the oxygen being about 5 trillion times less dense than Earth's atmosphere at sea level. While incredibly thin, the mere presence of this atmosphere raised intriguing questions about its origin and sustainability. One theory suggests that the oxygen is produced by the decomposition of water ice on Rhea's surface when it's struck by ions from Saturn's magnetosphere. The carbon dioxide, on the other hand, is thought to be the result of organic molecules on the surface being oxidized by the oxygen in the exosphere. This discovery made Rhea the first moon known to have an oxygen atmosphere other than Jupiter's moons Ganymede and Europa. It also opened up new avenues for research into the complex interactions between Saturn's moons and the planet's powerful magnetosphere. Rhea's exterior is fascinating, but what about its interior? Let's dive deeper, literally. While we can't directly observe what's beneath Rhea's icy surface, scientists have used various methods to infer its internal structure. Based on Rhea's average density of 1.236 grams per cubic centimeter, which is only slightly higher than that of water, we can deduce that Rhea is composed primarily of water ice, about 75%, and a smaller fraction of rocks, the remaining 25%. Rhea has often been described as a frozen, dirty snowball due to this structure. This puts Rhea in stark contrast to moons like our own moon, which are primarily rocky bodies. When Cassini visited Rhea, the probe's instruments also provided valuable data about Rhea's composition. Spectroscopic observations confirmed that water ice is the dominant component of Rhea's surface, but they also detected the presence of other materials. One surprising discovery was the detection of carbon dioxide trapped in the surface ice. This finding suggests that Rhea's ice isn't pure water, but contains other compounds, possibly including complex organic molecules. Due to its higher moment of inertia, most scientists believe that Rhea is not differentiated into layers. Instead, it is thought to be a homogeneous mix throughout, with the exception of its core. Some scientists challenge this model though. In 2006, a paper was released in the journal Icarus that suggested that Rhea might have a layer of liquid water under its surface, a subsurface ocean. While this idea is still highly speculative and not as well supported as the subsurface oceans on moons like Europa or Enceladus, it's an intriguing possibility that future missions might investigate. The presence of such an ocean would have significant implications for Rhea's potential habitability and of the conditions necessary for liquid water in the outer solar system. Rhea's interior contains mysteries, but one of the puzzling features of Rhea is its shape. While many large moons and planets tend towards a perfect sphere due to their own gravity, Rhea is noticeably non-spherical. It's slightly flattened at the poles and bulges at the equator, a shape we call a traxial ellipsoid. What's strange is that Rhea's shape doesn't quite match what we'd expect based on its rotation rate. This discrepancy has led scientists to propose that Rhea might have a non-uniform internal structure, with denser material concentrated away from its center. Now, let's talk about one of the most exciting moments in Rhea's recent history, the Cassini mission's close flybys. The Cassini spacecraft, a joint project of NASA, ESA, and the Italian Space Agency, spent over a decade studying the Saturnian system, including several close encounters with Rhea. The closest of these flybys occurred on the 11th of January 2011, with Cassini passing a mere 76 kilometers above Rhea's surface. The last close flyby was on the 9th of March 2013, when Cassini passed just 997 kilometers above Rhea's surface. This close approach allowed the spacecraft to capture incredibly detailed images of Rhea's crater terrain and gather valuable data about the moon's composition and determine it does not have an internal magnetic field. These flybys provided us with our best look yet at Rhea's surface features. They imaged a landscape dominated by two types of terrain, heavily cratered regions and younger, smoother plains first shown in earlier Voyager missions. The heavily cratered areas we mentioned earlier are thought to be extremely old, possibly dating back to the early days of the solar system. These ancient surfaces provide a record of the intense bombardment that occurred in the solar system's youth. The smoother plains, on the other hand, are likely the result of a resurfacing event, such as from material ejected from large impact events. This material would have fallen back to the surface, filling in older craters and creating smoother regions. But perhaps one of the most intriguing results from the Cassini mission was what it didn't find. Prior to Cassini's arrival, some scientists had proposed that Rhea might have a system of rings. This idea was based on unusual measurements of electron densities around Rhea made by Cassini in 2005. However, despite careful searches during its flyby, Cassini found no evidence of rings around Rhea. This non-detection doesn't completely rule out the possibility of some kind of debris disk around Rhea, but it does make it much less likely. Another intriguing aspect of Rhea is its place in Saturn's complex system of moons. Rhea orbits Saturn in what is known as the E-ring, a diffuse ring of ice particles thought to be supplied by the cryovolcanic eruptions from Enceladus. While Rhea itself doesn't seem to be geologically active like Enceladus, its position in this ring means it's constantly interacting with these ice particles. Although Rhea is in the extremities of the E-ring, beyond where it is dense, over time this interaction could affect Rhea's surface properties and contribute to the moon's bright appearance. As we reflect on what we've learned about Rhea, it's clear that this moon, often overshadowed by its more famous siblings, is a fascinating world in its own right. From its heavily cratered hemisphere to its relatively smooth side, from its tenuous atmosphere to its place in Saturn's complex system of moons, Rhea continues to intrigue scientists and spark our imagination. But our exploration of Rhea is far from over. Many questions remain unanswered. What is the exact nature of its interior structure? How has it evolved over the billions of years since its formation? Could it harbor simple forms of life in a hypothetical subsurface ocean? These questions and more await future missions to the Saturnian system. While there are currently no planned missions specifically targeting Rhea, the moon is likely to be observed by any future spacecraft sent to study Saturn and its moons. As we conclude our journey to Rhea, let's take a moment to appreciate the diversity of worlds in our solar system. From the scorching surface of Venus to the icy plains of Pluto, from the towering volcanoes of Mars to the potential subsurface oceans of icy moons like Enceladus, our cosmic neighbour is filled with wonders waiting to be explored. Rhea, with its icy surface reflecting the distant sunlight, stands as a testament to the beauty and mystery of our universe. As we continue to explore and learn, who knows what secrets this distant moon may yet reveal. You might not know much about Tethys, but you should know this. The moon called Tethys is a survivor. An icy world orbiting Saturn at 295,000 kilometers, it may appear unremarkable at first, until you learn what it has endured and become amazed that it's even here at all. Take a closer look at its scarred surface, and you'll see what I mean. Not many moons house a gargantuan trench system that wraps around 3/4 of their body. A tectonic rupture so vast, it beggars belief for a world this size. And opposing it, a gigantic impact basin stares back. Evidence of a collision so violent it should, by all rights, have blasted this moon into fragments. What did this? And how did Saturn's 5th largest moon survive the onslaught? The answers lie in its frozen icy shell, and today they are coming to light. I'm Alex McColgan, and you're watching Astrum. Join me today as we delve into the history and geology of Tethys, Saturn's scarred survivor. Tethys' first observation came from Giovanni Domenico Cassini. Following his arrival at the Paris Observatory, Cassini, the man who centuries later had a well-known probe named after him, identified Tethys in 1684 alongside Dione, adding them to his count of Saturnian moons that already included Rhea and Iapetus. Following the custom of the time, these were initially dubbed the Sidera Laodicea, or Stars of Louis for King Louis XIV. But the name didn't stick, and in the 19th century, John Herschel proposed a naming convention drawing on the Greek Titans to tie in with Saturn, or Cronus, the Titans' king. Tethys, fittingly for a water-ice world, was named after a Titaness and sea goddess. And it is indeed icy. A key characteristic revealed by gravitational measurements, primarily from the Cassini spacecraft, is Tethys' remarkably low density, approximately 0.97 grams per cubic centimeter, or 0.97 times that of liquid water. As a result of this, Tethys' mass is less than 1% of that of our own moon, despite spanning 1/3 of its diameter. This extremely low value strongly indicates that Tethys is composed almost entirely of water ice, with a small amount of rocky material integrated within. It suggests Tethys likely never fully differentiated into a distinct rocky core and icy mantle, or if it did, the core is exceptionally small. The density might also imply some degree of internal porosity, meaning the ice within might not be perfectly compacted, potentially containing voids or less dense ice structures. This composition makes Tethys a quintessential example of an outer solar system ice world. Physically, Tethys presents a typically bright, icy satellite. Its high bond albedo, reflecting around 60% of incident radiation from the Sun, confirms a surface dominated by water ice, relatively free from significant amounts of darker, rocky or carbonaceous contaminants seen on moons like Iapetus or Phoebe. Tethys has an irregular shape, resulting from the gravitational influences of its neighbours. The classical sphere shape has been squashed into a triaxial ellipsoid, meaning that it has 3 axes. However, perhaps the most arresting feature on Tethys is one of its landmarks, Ithaca Chasma. This enormous canyon system dominates the moon's topography. It measures up to 2,000 kilometers long, 100 kilometers wide, and 5 kilometers deep. Now, I really want you to take a moment to grasp the size of this feature. Imagine a crack running from New York City almost to Denver, Colorado, and you start to grasp the scale relative to the moon's size. It dwarfs Earth's Grand Canyon and is proportionally one of the largest canyon systems in the entire solar system, rivaled perhaps only by Valles Marineris on Mars. The existence of such an imposing feature on a seemingly simple icy moon begs the question, how did it form? Several theories have been proposed, but the leading hypothesis connects Ithaca Chasma to Tethys' internal evolution, suggesting that it may have formed early in the moon's geological history. As Tethys formed and subsequently cooled, any liquid water within its interior would have begun to freeze, and unlike most substances, water expands when it freezes. If Tethys once possessed a substantial subsurface ocean, or even just a partially liquid interior, the gradual solidification of this water would have caused the moon's volume to increase like an inflating balloon. This expansion would have placed immense stress on the rigid, outer, icy crust. Ithaca Chasma, according to this theory, is the result of the crust cracking and splitting apart under this relentless internal pressure, a global scale stretch mark signifying the moon freezing solid from the inside out. The sheer scale of the chasma suggests that Tethys might have expanded laterally by around 5% during this process, which is crazy to think about. An entire moon swelling up until it literally began to burst. Other theories have considered links to the giant impact crater, Odysseus, suggesting the shock waves might have fractured the opposite hemisphere. However, the chasma is thought to be older than the Odysseus basin, and detailed modelling suggests the expansion freezing model provides a better fit for the observed geology. Ithaca Chasma, therefore, isn't just a spectacular sight. It's a record of Tethys' thermal history, a dramatic indicator that this now frozen world may once have undergone growing pains on a cosmic scale. Surface temperatures on Tethys are incredibly low, averaging around minus 187 degrees Celsius, ensuring water ice remains brittle and stable against sublimation, except over very long geological timescales. It's cold enough there that the water ice on Tethys can often act like rock. Tethys lacks any detectable atmosphere, leaving its surface directly exposed to the harsh environments of space. Micrometeoroid impacts, solar radiation, and charged particles within Saturn's magnetosphere. Only, not all of those micrometeoroid impacts were micro. One was large enough that it nearly shattered frozen Tethys like a bullet through a snow globe. It's time to take a look at the Odysseus crater. If Ithaca Chasma speaks to internal forces, the Odysseus crater screams of external violence. Located on Tethys' leading hemisphere, Odysseus is the moon's largest impact basin, measuring approximately 450 kilometers across. That's more than 2/5 the diameter of Tethys itself. The impact responsible for this enormous feature was thought to have occurred between 400 million and 1 billion years ago, and judging by the size of the crater compared to its moon, if Tethys had been icy and hard like it is now, there is a significant chance Tethys would have been broken into pieces. But it seems the impact occurred when Tethys' interior was still partially molten or slushy, allowing it to absorb and dissipate the impact energy more effectively than the completely solid, brittle body could have. An unlucky break. Interestingly, Odysseus is remarkably shallow for its diameter. Unlike the sharp, ball-shaped craters we see on rocky bodies like our Moon or Mercury, Odysseus is relatively flat, its rim subdued, and its central peak complex largely collapsed. This is not how it would have looked immediately after the impact, and suggests a phenomenon known as viscous relaxation was at play. Over geological timescales, even solid ice behaves somewhat like a very thick fluid, especially when topography is significant. The immense depression created by the impact and the uplifted rim would have slowly slowed and slumped under Tethys' own gravity, gradually smoothing out the crater's profile. The degree of relaxation observed in Odysseus provides further clues about the thermal state and composition of Tethys' crust at the time of the impact and in the eons since. Which makes sense. Like a nuke suddenly detonating, such a large impact tends to release a lot of energy, and it would seem logical that not everything would remain icy. The impact likely resurfaced a significant portion of the surrounding terrain, either obliterating all the craters or smothering them with its ejecta. So, Tethys has taken some hits over the years, both from within and without. But that's not all there is to this moon made of ice. Another notable discovery from Tethys was its unusual thermophysical properties, which, amusingly, tied it to a 1980s computer game character. In 2015, Cassini's composite infrared spectrometer made a series of observations of Tethys' daytime anti-Saturn hemisphere over a 9-hour time period. This produced data to confirm an anomaly that had previously been identified in 2012, that the lower latitudes of Tethys' leading hemisphere appear cooler in the day and warmer at night compared to the surroundings. This area of Tethys also appeared darker in infrared and UV color ratio maps when compared to the rest of the leading hemisphere. Funnily enough, the pattern, when mapped out, made the moon look like a giant Pac-Man, which gave scientists a good chuckle, and proving their sense of humor, they gave this phenomenon the same name. Still, the Pac-Man heat mapper on Tethys and a similar one on neighboring Mimas needed an explanation. Tethys orbits Saturn at a distance of about 295,000 kilometers, making it the 5th largest moon in the Saturnian system. Its orbital period is short, just under 1.9 Earth days, and like most major Saturnian moons, it is tidally locked. Why does this matter? Well, this gravitational interaction ensures Tethys perpetually presents the same hemisphere towards Saturn, dividing its surface into a leading hemisphere facing the direction of orbit and a trailing hemisphere. This helps keep Pac-Man facing the same direction, which also brings us to its color. The leading hemisphere, facing the direction of orbit, appears to be between 10 to 15% brighter than the trailing hemisphere, and its near-infrared spectrum suggests that it has more pure water ice on its surface. This pattern is generally attributed to external factors. The leading hemisphere is the side that gets exposed the most to weathering by particles from Saturn's E-ring and Enceladus' plumes. This weathering will sandblast material onto the surface of the leading hemisphere, which tends to consist of submicron-sized icy particles. Smaller water ice particles reflect more light than larger particles, therefore giving the leading hemisphere a higher albedo. The trailing hemisphere, conversely, is more heavily bombarded by energetic plasma particles trapped within Saturn's magnetosphere. This high-energy radiation can sputter surface molecules, break chemical bonds, and implant ions, processes collectively known as space weathering, which tend to darken and redden icy surfaces over time. Contamination by micrometeoroids carrying darker material could also play a role. In other words, we now think that Saturn's rings are to blame for feeding Pac-Man, as the differential bombardment from E-ring particles across the moon's leading hemispheres modify the surface. This will give certain regions a higher thermal inertia, meaning they store and release more heat effectively than their surroundings, therefore creating the observed temperature differences. It's a pretty fun finding, one that makes you realize just how much these moons are shaped by their unique interactions with Saturn's rings. Tethys may lack the atmospheric complexity of Titan or the obvious present-day activity of Enceladus, but it is far from a boring, inert world. It is a body profoundly shaped by extreme events. Its story is writ large across its surface in the form of Ithaca Chasma and the Odysseus crater. It is also an incredible example of how worlds and moons are influenced by their wider neighborhoods. Tethys is icy, but the subtle variations in its surface texture and color hint at ongoing interactions with the Saturnian environment. Traveling around Saturn and its rings changes Tethys, and studying the two helps us better understand these dynamic interactions. Sadly, there are no new missions to Tethys currently planned, but Tethys has survived worse fates. It has been squeezed, it has been sandblasted with icy dust, and it has been struck from above with forces that could have shattered it. Tethys is a survivor, and although its crust is made of ice rather than rock, it is unapologetically hardy. It has weathered anything the universe has thrown its way so far, and will keep going strong. Well everyone, here it is, your most asked for video. Titan. And to be fair, I can understand the curiosity towards it. It is the only moon with a substantial atmosphere. There is clear evidence of stable bodies of surface liquid on it. And best of all, mankind has visited it, so I will be able to show you a lot of real photos and video footage. I'm Alex McColgan and you're watching Astrum, and here is everything you could want to know about Saturn's biggest moon, Titan. But let's start from the beginning and give some context to this remarkable planet-like place. Titan is the sixth spherical moon from Saturn, and unlike Jupiter's 4 Galilean moons, in the Saturn system, Titan is all by itself in its size. The rest of Saturn's moons are pretty small in comparison. To give some idea of how big it is, Titan's diameter is 50% larger than Earth's moon and is 80% more massive. In fact, it's the second largest moon in the entire solar system, after Jupiter's moon Ganymede. It does actually appear slightly bigger than Ganymede if you were to put them directly side by side, but this is caused by Titan's thick atmosphere, which extends its apparent diameter. Even so, Titan's real diameter is still larger than the smallest planet, Mercury, but it's only 40% as massive. As its density is quite low for its volume, its gravity is reasonably weak, at only 0.14 Gs, or 1.35 meters per second squared, which is even less than our moon. Due to Titan's low density, it is thought that its composition is half water ice and half rocky material, and like other celestial objects this size, it is believed Titan has a differentiated interior. This means it has layers, and like a lot of other large moons, one of those layers is thought to be a liquid ocean comprised of water and ammonia under the moon's crust. This liquid ocean is comparable to Earth's magma layer, situated between the core and the crust, and has been made liquid due to heat, pressure, and to a certain degree, tidal forces. The existence of this liquid layer was proven more likely when Cassini, the spacecraft orbiting Saturn, discovered extremely low-frequency radio waves in Titan's atmosphere. Titan's surface is not known to be a good reflector of low-frequency radio waves, but the liquid interior would be. Another reason is that the surface features on the moon have shifted by up to 30 kilometers since Cassini started observations, which could imply that the surface is not attached to the core, but is rather floating on this liquid ocean layer. And while there is no evidence of life on Titan, scientists do speculate that the conditions would be right for there to be life in this subsurface ocean. Unfortunately, if there was life to be found on the surface or below, we'll have to wait a while, as there are no planned missions to check out this possibility, and Jupiter's Europa is a more likely candidate to be investigated for life in the foreseeable future. The differentiated interior of Titan does not produce a magnetic field. Titan is still quite protected from the solar wind though, as 95% of its orbit around Saturn is within Saturn's own magnetosphere. Titan orbits Saturn once every 15 days and 22 hours, and has a rather large orbital eccentricity, which means the orbit isn't so circular. Its orbital plane is also at an angle, but that doesn't mean that Titan is likely a captured object. Rather, like Jupiter's Galilean moons, it is thought that Saturn also had several large moons in the past, but most of these had been destroyed through big collisions, which left Titan the lone victor. Saturn's medium-sized moons, like Iapetus and Rhea, are thought to be the remnants of this tumultuous beginning. Titan's day, like the day on our moon, is identical in length to its orbital period. This means Titan's rotation is tidally locked to Saturn, and only ever shows one face to the planet. Not that visually it makes any difference. Titan's hazy atmosphere completely blocks the view of the surface from an outside perspective. On the other hand, you might just be able to see Saturn while standing on Titan, although the view would be significantly obscured. This does mean, however, that if you were to stand on one spot on Titan, Saturn would never move in the sky. Removing Titan's haze, this is what it would look like. This leads us on to one of the topics that truly sets Titan apart from the rest of the moons in the entire solar system, its substantial atmosphere. I remember the first time I ever saw a photo of Titan, I was truly blown away, as it never occurred to my young self that the moon could even have an atmosphere. I thought it must have been a new planet they'd discovered recently or something. To me, what looks odd about the atmosphere is how far it stretches into space. When you see a picture of Earth, you see that the atmosphere has quite a tight fit around the planet. Titan, on the other hand, looks like it has a thick blanket all over it. There are a number of reasons for this. The first one is that Titan is a lot smaller than Earth, but its atmosphere is 1.9 times more massive than Earth's, or 7.3 times more massive on a per surface area basis. The second reason is that Titan's gravity is a lot weaker than Earth's, meaning it doesn't pull it down as strongly. The mass of the atmosphere actually means the pressure at the surface is 1.45 atmospheres, or 45% more than the atmospheric surface pressure on Earth. And comparing the two, you can see the extent of how far Titan's atmosphere stretches into space. 600 kilometers high is only the limit of the mesosphere. Earth's mesosphere, on the other hand, stops at 120 kilometers. Even at a distance of 975 kilometers, the Cassini spacecraft had to make adjustments to maintain a stable orbit against atmospheric drag when it made its closest approach. Like Venus, Titan is a super rotator, meaning its atmosphere rotates faster than the rotation of the planet. This can especially be seen at the poles on the moon. Each pole has a polar vortex that rotates once every 9 hours, compared to the moon's rotation of 16 days. The vortexes on each pole seem to be like permanent hurricanes. So what does the atmosphere consist of, and why is it orange in colour? Well, the atmosphere is 98.4% nitrogen, the remainder being mainly methane and small amounts of hydrogen.
There are also trace amounts of hydrocarbons from the breakup of methane in the upper atmosphere due to UV light, and it is these hydrocarbons that are thought to give Titan its orange hue. This constant breakup of methane to hydrocarbons should have meant the moon ran out of methane within 50 million years, a very short space of time compared to the age of the solar system. This means there must be a source that replenishes the methane, the most likely candidate being cryovolcanoes, although biological life has not been ruled out. The methane in the atmosphere creates a greenhouse effect, without which the temperature on Titan would be a lot lower. Conversely, however, the haze also reflects a lot of the sunlight, creating an anti-greenhouse effect, which cancels out some of the potential greenhouse effect from the methane. Now, while Titan's upper atmosphere gets 1% of the sunlight Earth does due to the distance from Titan to the Sun, another result of this reflection of sunlight means the surface of Titan only gets about 0.1% in the end. The Huygens team liken the difficulty of taking photos at this light level to taking pictures of an asphalt parking lot at dusk. All these things combined means that while it would be dark, a human would only need an oxygen mask and to wrap up extremely warm to be comfortable while standing on the surface of Titan. It really is cold on Titan, minus 180 degrees centigrade on average. This means any water on Titan remains solid and doesn't ever melt, evaporate, or sublime. Then why are there sometimes clouds on Titan? Well, these are not water ice clouds, but rather methane clouds, which means yes, it can rain methane on Titan. In fact, the temperature on Titan is just right for methane to be liquid. Methane freezes at minus 182.5 degrees centigrade and boils at minus 161.5 degrees centigrade. The temperature, combined with the surface pressure, got scientists very excited at the prospect of there being hydrocarbon lakes or seas on the surface of Titan, similar to water lakes and seas on Earth. If there really were lakes on this moon, it would be the first time this had ever been observed outside of Earth. This was actually one of the main driving forces behind Cassini-Huygens, to see what there was under that thick atmosphere. The Huygens probe, named after the astronomer who discovered Titan in 1655, was designed to enter Titan's atmosphere and land on the surface. The possibility of even landing on an ocean was taken into account during its design process. As the probe descended, its parachute was pulled, and after an almost 3-hour journey, it finally rested on the solid surface of Titan. Sadly, it wasn't able to see any lakes, but what it did see confirmed that methane lakes once existed, as Huygens landed on what appeared to be a dried up lake bed. These stones you see from the surface photos are rounded stones, much like pebbles found in a river or a lake on Earth. Cassini, from the perspective of space, was able to confirm that methane lakes are still found on Titan today. Near the South Pole, Cassini observed an area which was later confirmed to be a lake called Ontario Lacus. It is 20% smaller than its North American namesake, Lake Ontario. So in other words, it is still pretty big at 15,000 square kilometers. On this side of the lake, you can see a smooth shoreline eroded by waves. On the west side, you can see the first evidence of a river and delta on Titan, meaning that liquid hydrocarbons flow down higher plains to the lake, leaving delta deposits in much the same process you would find on Earth. Ontario Lacus is extremely shallow, only estimated to be between 40 centimeters and 3 meters deep, the deepest point likely to be just over 7 meters. As Cassini's radar mapped this lake, it found that the lake did not have waves bigger than 3 millimeters, meaning the surface would appear like a sheet of glass or a mirror. This doesn't mean there can't be bigger waves, unless this liquid is particularly viscous, but the likelihood is that it was simply not a windy day as the observations were taken. The atmospheric density and gravity on Titan should mean that waves would be bigger on Titan than they would be on Earth. As the north pole of the moon began to come out of a 15-year winter, another lake was discovered, Jingpo Lacus. As Cassini was passing by the moon, sunlight was reflected off the surface of Jingpo Lacus like a mirror, directly into the view of Cassini. Upon further observation, Cassini was able to detect further evidence of moving liquid on Titan, as can be seen by these rivers flowing into the lake. The second biggest lake on Titan to be discovered is Ligeia Mare. Found in the North Polar region of Titan, it is bigger than Lake Superior on Earth, with a surface area of 126,000 square kilometers. While parts of this lake are reasonably shallow, the average depth is a lot deeper than Ontario Lacus at 50 meters, and some parts of it could reach depths of over 200 meters. Plenty of rivers can be seen flowing into the lake, and there are large islands found around this area here. A particularly curious observation Cassini made, dubbed the Magic Island, is the appearance and disappearance of what appears to be an island. Although scientists are unsure exactly what happened here, the theories are that it could be silt suspended in the lake, bubbles, or subsurface ice rising to the surface as the lake warmed during the moon's spring. But still very curious. The largest lake on Titan, at 400,000 square kilometers, is the Kraken Mare. As you can see, the lake is split up into two main parts, separated by a small stretch quite similar to Earth's Strait of Gibraltar. Its nickname is the Throat of the Kraken. Because of tidal forces and the size of the lake, it's thought the tide changes by about 1 meter, and so this strait may have strong currents and even whirlpools. The Kraken Mare is also quite deep in comparison to Ontario Lacus, but isn't any deeper than 170 meters. So, we know about the lakes on Titan now, but what other interesting surface features might it have? Well, plenty actually. Titan's surface is quite young as 100 million years old, which means its surface must be geologically active. Some scientists believe the dirty ice crust is substantially rigid, although there is some evidence to suggest that there is tectonic activity on the moon, possibly caused by tidal forces with Saturn. The main factor of a renewed surface, however, is likely to be the same thing that produces methane in the atmosphere: cryovolcanoes. Now, this is pretty interesting. You know how magma on Earth is pretty hot, but when it comes out of the ground it freezes. Well, Titan has the same thing, except its magma is water and ammonia, and when it comes out of the cryovolcanoes and spills over the land, it too freezes to renew the surface. Because a water and ammonia blend is a lot less viscous than lava, it flows further than lava on Earth. This means mountains are more flat and will never reach the heights of volcanoes on Earth. While it is hard to confirm specific cryovolcanoes on Titan due to the obstruction caused by the atmosphere, the most likely candidate is Sotra Patera, found on the southern hemisphere. In this image, height has been exaggerated by a factor of 10, but it gives a good idea of the sides of the dome and the 1.7 kilometer deep pit, the largest that we know of on Titan. The force necessary for this to erupt would have had to have been incredible, and while it doesn't appear to be active now, it is being actively monitored. The fact that lava on Titan is a mix of water and other minerals means the surface could be compared to dirty ice. Because we know the Huygens bounced and wobbled in a certain way as it landed on Titan, we have a rough idea of what the consistency of the surface could be like. Scientists have referred to it as a soft, damp sand. Another theory is that it's like snow with a thin crust on top. Imagine walking on frozen snow. If you're careful, you can walk on a solid surface, but if you stomp too hard, you will sink in quite deeply. And Titan's believed to be something like this. Titan's highest mountains come in the form of ridge belts, like the Rockies in America. These ridge belts could also be a form of cryovolcanoes. The largest mountain on Titan can be found in one of these mountain ranges, known as Mithrim Mons, and is 3,337 meters high. Interestingly, mountains this tall are thought to be topped with methane snow. Also found on Titan are many gorges, valleys, and dunes. Using infrared cameras to see the surface from space, what can also be seen quite prominently are these large patches of dark terrain. Originally, these dark patches were thought to be seas until the Huygens probe landed on one of those areas, known as Shangri-La, They could well have been seas in the past, but now they are plains of dark mineral deposits, similar to the Namib Desert on Earth, where they appear as windswept dunes in some places. Overall, Titan can be compared to Earth in lots of ways. Scientists think that Titan shows signs of what early Earth could have been like, only much colder. It's fair to say that Titan is remarkably interesting, and I can only hope it gets its own mission one day. Cassini has done a great job, but it was never a Titan orbiter, and its mission will soon be over anyway. What I would find extremely fascinating is to explore more of its surface, and hopefully it won't be long until a mission to do that will be approved. Until then, here was everything you could want to know about Titan.
It's been 3 years since Cassini ended its mission by diving into the atmosphere of Saturn. Its mission was tremendously successful, and it was, in my opinion, one of the greatest missions of all time. The data it collected over the 13 years in orbit around Saturn is still being pored over today, as there are still a lot of unsolved mysteries about Saturn and its moons. One of the most impressive discoveries of Cassini was confirming the existence of liquid methane lakes on the solar system's most unusual moon, Titan. But knowing they are there didn't help answer how they came into being. But now, scientists may have come up with an answer. I'm McColgan and you're watching Astrum, and today we will explore everything we know about Titan's lakes, what Cassini has seen and discovered, and how we now think they came into being. There are only 2 places in the solar system that have stable bodies of liquid on their surfaces, Earth and Titan. That doesn't mean they are very similar places though. Earth is a rocky planet with an iron core and silicate mantle. Titan is an icy world. Its crust and mantle are made up of mainly water ice, with a subsurface ocean of water surrounding a rocky core. This means Earth is much denser, and, coupled with its bigger size, means the gravity on Earth is a lot stronger than on Titan. Both worlds have dense atmospheres, but due to their differences in gravity, Earth's atmosphere hugs the planet tightly. While Titan's, although a little more massive in total than Earth's, stretches hundreds of kilometers above the moon's surface. Their compositions are also different. Earth is much closer to the sun, meaning it is much warmer than Titan, which allows there to be an active water cycle. Water is frozen on Titan. However, the temperature is just right for liquid methane to be present on its surface. That means, yes, Titan experiences a methane cycle in a similar fashion to Earth's water cycle. Methane clouds have been spotted in Titan's atmosphere, and these clouds rain liquid methane onto Titan's frigid surface. This process carves out rivers through the surface ices that flow into small seas or lakes. Radar data from Cassini, visualized in these images, clearly show various riverbeds and valleys cut away by the flowing methane. The most prominent of these flow channels are found around Titan's second largest lake, Ligeia Mare. These channels, dubbed Vid Flumina, are special because they look to be much older than any other flow channel on the moon. The canyons have walls hundreds of meters tall with very steep slopes. Liquid methane is visible in the canyon, but right now it isn't flowing. Rather, it is likely to be a drowned river valley due to the level of Ligeia Mare, although some higher altitude tributaries are likely to still be flowing down into the canyon. The lakes on Titan can be huge. The biggest one, the Kraken Mare, is bigger than the Caspian Sea on Earth at roughly 400,000 square kilometers. The radar data suggests that a lot of these lakes are very shallow, some of them only a few meters deep. Some of the larger ones, however, can have depths of over 200 meters. All in all, this puts the total amount of potential fossil fuels on Titan to over 300 times the proven amount on Earth. The lakes of Titan are surprisingly still. Some lakes do not have ripples larger than about 1 millimeter, meaning it would appear like a glass or a mirror. This came as a surprise to scientists, who expected waves of up to 1 meter in height due to the low gravity and dense atmosphere blowing over the surface.
This could mean that there just so happened to not be any wind as Cassini passed over, the lakes are a lot more viscous than expected, or that they occasionally freeze over. One other theory has been proposed, and that is that dense aerosols may sit on the lake's surface, creating a film which prevents waves from forming. The detection of lakes on Titan couldn't be possible without the aid of Cassini's radar instrument and infrared camera to see through Titan's thick haze. These instruments use a process called specular reflection to make observations. The radar instrument detected large dark patches across the surface, which were later confirmed to be lakes by the infrared camera, when sunlight reflected off the lake and into Cassini's view. A bit like what you sometimes see of Earth from space. Specular reflection with the infrared camera and the sun ended up being used a lot to confirm what the radar secular reflection was seeing. Interestingly, clouds and the subsequent effects of their rain were also detected. In the left image you see a light patch indicating dry ground, but a year later the area was imaged again, and this time darker patches can be seen, indicating a very flat surface, highly likely to be shallow and small lakes. The lakes aren't distributed evenly across the moon, rather most of them are found near the poles. However, the Huygens probe, which was part of the Cassini mission and landed on Titan's surface near the equator, did see flow channels around the equator too. But where are the lakes these channels would flow into? Well, this is thought to be the result of seasonal variations, like summer and winter producing different types of weather on Earth. At certain points in Titan's year, rain would fall in these parts and pool on the surface. However, these probably evaporate during the rest of the year, and the rain migrates to the north and south, which is what Cassini and Huygens would have observed. Even though Cassini was in orbit around Saturn for 13 years, that's not even 1/2 of a Saturnian year. Saturn takes a full 30 Earth years to orbit the Sun once, so Cassini didn't capture a complete picture of all the seasonal variations. The lakes likely vary in depth throughout the year, with some potentially drying up completely. There is one other mystery that was thrown up by the Cassini data to do with Titan's lake that may have recently been solved. Some of Titan's smaller lakes have very steep rims that tower above the lake level. This is unusual, as lakes on Earth typically form from erosion processes and dissolving limestone, meaning the rims are shallow and smooth. These are called karstic lakes. But this process doesn't add up for a number of Titan's lakes. Scientists now believe that these could be explosion craters that have since filled up with liquid methane. Models suggest that Titan was once colder, with nitrogen rain and snow instead of methane. This liquid nitrogen would have seeped into the crust, creating pockets of liquid nitrogen. As the greenhouse gas methane was pumped into the atmosphere by cryovolcanoes in Titan's past, the world warmed and would have caused the liquid nitrogen now trapped under the surface to evaporate and expand, building the pressure in the pocket until the lid basically blew off, leaving an explosion crater. There is still a lot to be learned from the Cassini data. The lakes of Titan were just a small aspect of the mission, and scientists are going to be piecing these puzzles together for years to come, better understanding the Saturn system as a whole. I really hope future space agencies will be as ambitious and as successful as the Cassini mission. There is still an awful lot to discover out there. Enceladus. Perhaps one of the most intriguing objects in the entire solar system. And yet it is only the 6th largest moon of Saturn, and in natural light it looks very unassuming. However, there's a lot more to Enceladus than meets the eye. It's an active, icy world with jets of water vapor pouring out from its southern hemisphere. Thanks to the remarkable Cassini mission, we have studied and observed Enceladus in exquisite detail, and perhaps know more about it than some of the closer and bigger Jovian moons. However, although we've seen a lot from the outside, it's the inside of the moon that still holds so many mysteries. I'm Alex McColgan and you're watching Astrum, and together we will explore some of the most fascinating details of Enceladus,
piecing together photos and data from a variety of missions to find out almost everything you could want to know about this special moon. So stick with me on this journey of discovery. Let's first of all discuss where Enceladus fits into our solar system. Enceladus is currently Saturn's 14th closest moon. I say currently, as Saturn has some tiny moonlets hidden in its rings that may or may not be classified as moons in the future. It is the second closest major moon though, second only to Mimas. That means that its orbit takes it just outside of Saturn's major rings. Its orbit follows the planes of the rings very precisely, and it only takes 33 hours to orbit Saturn once. Interestingly, it is in a 2-1 orbital resonance with Dione, Saturn's 4th closest major moon. In other words, it orbits twice around Saturn in the time Dione orbits once. This orbital resonance is believed to prevent Enceladus' orbit from ever becoming perfectly circular, which causes Enceladus to undergo tidal deformation. This is significant, as these tidal forces heat up Enceladus' core. You see, as far as we can tell, Enceladus' surface is predominantly made of clean water, certainly with little to no rocks or much else there. Because Saturn is situated so far away from the Sun, it means the outer layer of water on Enceladus has frozen over. Enceladus is essentially a frozen ocean world, a giant ball of water ice. Because it is free from other materials on the surface, the Moon is one of the whitest objects in the solar system, with a bond albedo of 0.81, which is pretty much as high as snow. As such, it is one of the coldest satellites of Saturn, with a noon temperature of -200 degrees Celsius, as the white color of its surface reflects a large percentage of the sunlight reaching it back into space. However, about 30 to 40 kilometers down under the surface of Enceladus, pressures start building, and heat energy generated from the tidal deformation of its orbit has increased the temperature of the water ice to the point where the water at this depth can exist in a liquid form. It could well be that there is an entire mantle or a global ocean of water that the ice crust is resting upon, very much like the magma mantle that our rocky crust on Earth rests upon. At the very least, scientists expect there to be a huge pocket of water under the Moon's south pole. How do we know this? Well, the most obvious indication are the huge plumes of water being ejected from the cracks in the crust, something referred to as water or cryovolcanism. These jets are really active, consistently blasting around 250 kilograms of water into space every second at speeds exceeding 2,000 kilometers per hour. This is powerful enough that most of the water vapor particles escape Enceladus' weak gravity, and they end up in orbit around Saturn, forming Saturn's E-ring. This ring around Saturn is very diffuse, and so isn't really visible unless it is backlit by the Sun. From this angle, the light shining through the water particles make the ring appear exceptionally blue. In fact, this ring is considered the bluest object in the solar system, even more so than Neptune due to the ring's uniformity. The E-ring is Saturn's second outermost ring, and it is 2,000 kilometers wide. Its shape is also heavily influenced by the orbit of Enceladus. Enceladus's plumes create tendril shapes in the rings as more material erupts out of it. However, these sections of the ring tend to smooth off as Enceladus moves further away along its orbit. During the course of Cassini's mission, Cassini was able to pass through these plumes to detect the substances being ejected from them. Cassini wasn't designed with this in mind. Scientists didn't know about the plumes until Cassini got there. However, Cassini was equipped with an instrument called the Cosmic Dust Analyzer, designed to detect what the tiny dust grains in orbit around Saturn are made of, and it was able to use it for Enceladus's plumes too. As it wasn't specifically designed with this in mind, it might not have given us the full picture of what's in these particles, but while water was the predominant substance detected, amino acids, carbon dioxide, nitrogen, and methane were also found. Amino acids are significant as they are the building blocks of life and can be found around the thermal vents at the bottom of Earth's oceans. Does this mean Enceladus has thermal vents of its own? And if so, do they have ecosystems of life around them? While evidence for an underground ocean is abundant, scientists still aren't completely sure about Enceladus' internal structure. At some points in the past, scientists believed that Enceladus was water all the way through. However, data from Cassini suggests that Enceladus' mass is in fact greater than previously thought, meaning it must have some amounts of iron or silicate material in its core. Scientists are starting to lean towards the theory that the internal structure is differentiated, meaning it's a celestial body with defined layers within it. An object of this size really doesn't have to be differentiated. In fact, it's so small at only about 500 kilometers across that it is right on the borderline of being in hydrostatic equilibrium, or in other words, being rounded by its own gravity. There are a number of objects out there of similar or smaller sizes that are not in hydrostatic equilibrium, like Neptune's Proteus. In any case, assuming it does have a differentiated interior, this core is likely to be predominantly rocky. This is important, as thermal vents in Enceladus' water ocean would have to come from a rocky core. A rocky ocean floor would also provide nutrients and minerals essential for what we believe life would need to form and evolve. Thermal activity clearly does exist due to the way Enceladus has plumes in the first place, and the amino acids detected in the plumes suggest a rocky core. As Cassini passed over Enceladus, it also mapped out the thermal emissions from the moon. It turned out that the jets line up with what has come to be known as Enceladus' tiger stripes. These are large depressions, roughly 130 kilometers long, 2 kilometers wide, and 500 meters deep. It is believed that these are tectonic fractures in the moon's icy crust. What is really interesting about the surface features of Enceladus is that there are virtually no impact craters at all over the southern hemisphere, and not many anywhere else. This implies that Enceladus' surface is very young, as while it does have a thin atmosphere made up from the ejected water from the plumes, this isn't nearly enough to burn up asteroids before they hit the surface. Some water from the plumes obviously settles again on the surface, which smooths it off over time. This is another reason why Enceladus is so round for such a small celestial body. In fact, apart from the tectonic fractures and few craters, Enceladus' topographical variation is really quite minimal. There are no mountain ranges to speak of, although there is what you might call a rough terrain around the South Pole if you zoom in far enough. This is perhaps the highest resolution image we have of its surface, and as you can see, it really does appear like a giant glacier. It's interesting to note that even in this small view, there are some smooth sections of ice, but also jagged regions. Over the North Pole, the clear difference is the number of craters present there. While there are tectonic fractures here too, there are no plumes on this side of the moon, so the surface here is clearly a lot older than around the South Pole, which is why it has more of a cratered surface. As Cassini flew through the plumes around the South Pole, it also took the opportunity to image the surface closely around the tiger stripes. The surface here is pretty incredible, unlike anything you would have seen on Earth. It's like the surface has been folded, squashed, and shifted around, leaving these remarkable fracture lines and formations in the surface ice. The fact that Cassini was able to get so close to Enceladus is a feat in and of itself. It's fantastic that we can have such a close-up view of something so far away. Unfortunately though, since the Cassini mission has ended, we no longer have anything in orbit around Saturn that can study Enceladus further. There have been plenty of mission proposals in the past, but all of them were cancelled before they came to fruition. What would be incredible is a probe that could either make its way into Enceladus' ocean somehow, or at the very least, search the plumes for signs of life. There is already a mission called Dragonfly going to the nearby moon of Titan, however this won't have anything to do with Enceladus. So, although a couple of mission proposals are currently under review to go there, that means we are unfortunately still a couple of decades away at least, which is a shame, because who knows what secrets lie in wait under that crust. So, there we have it, a look at the intriguing little moon of Enceladus. I'm happy to announce we have a weekly newsletter to keep up with all the discoveries in our cosmos, and our designer Peter has made the most beautiful email you'll ever receive. Sign up with the link down below. It's the best way to stay connected between videos. Short, focused updates on what's new and fascinating in space each week. No spam, no filler, just the good stuff. You'll get the latest news, visuals, and insights delivered straight into your inbox. If you enjoy Astrum videos, you'll love this. Join the newsletter and stay curious with us.